Hello everybody. Hey, you know what? It is a rainy day here in beautiful New Smyrna Beach, Florida, and rather than not do anything with our flight students, we say, well, you know what? Maybe we can't fly, but we could do some FTD work, we could do some video work, we could do some ground instruction, or, you know what I'm gonna do? I'm gonna take some paper plates and cups, and we're gonna do a little art and craft, and I'm gonna show you the inner workings of the gyroscopic instruments by taking these two-dimensional diagrams and moving them into the three-dimensional world. That's right, everybody. This is the Instrument Ground School at the Epic Flight Academy, and I'm your host, Mike Thompson. So let's see if we can take a look at how these instruments actually work. Now, before we build our gyroscope models, we have to clearly understand the idea of a gimbal. And on this slide right here, you can see the graphic of a gimbal. Now, the gimbal has bearings on three different axes that hold the spinning rotor in place and allow that rotor, when it's spun up at a high speed, to maintain its rigidity in space. So we have to first understand the operation of a gimbal. That gimbal is connected to the inside of the instrument case, and the instrument case is, of course, bolted to the instrument panel, which is part of the airframe. So as the aircraft, the instrument panel, and the instrument case are moving, they are actually moving around that rotor or that gyro that's maintaining rigidity in space. So if you could imagine my hand here as that vertical gyro maintaining rigidity in space, and this hand as the instrument case literally moves around this gyro maintaining rigidity in space because of that gimbal. Now, that's an important first thing to understand. Once we know that, let's go back to this attitude indicator, and you can see the picture of it here. And let's look at this horizontally spinning gyro, and notice how it's mounted inside of its gimbal. Now, I'm going to take a paper plate, and I'm going to represent that horizontally mounted gyro spinning very quickly in this horizontal plane. Now, underneath of that gyro, the spinning portion is the rest of the gyro, and underneath of it, in this support piece, this gyro has 4 doors. Each one of these doors has a small hinging door in front of it. Do you see that? This little door is hinged and it tips with gravity. Now imagine each one of these 4 ports has that little door. In this case, this gyro is spun by a vacuum pump. The air from that vacuum pump is pulled across these discs right here, spins this at a high rate of speed, and then exits through that little space on the door there. See that? So it's exiting all 4 doors equally. This gyro is spinning rapidly in this horizontal plane, and it's maintaining its rigidity. All is well, that's my artificial horizon. But, what would happen if this gyro were actually accidentally or somehow upset off of its rigid plane? What's going on? How can we get it to come back to horizontal to be my artificial horizon? Well, this is how that happens. If it were upset, let's say like this door by gravity would open up. Can you see that? And now more air would be allowed to escape from this door, applying a small force right here. Now, that applied force would act 90 degrees in the direction of rotation, remember? Gyroscopic precession. So this applied force would act 90 degrees in the direction of rotation. It would come over here and it would act, tip it back to vertical, gravity would close the door, everything would be back in equilibrium. That's how this attitude indicator remains level. So take a paper plate and you can cut the edges, put in your direction of rotation, put a paper cup underneath of it, make yourself a small door, pin it on there with a pin, and you can move that two-dimensional diagram into a three-dimensional model, and you can see how we take advantage of gyroscopic precession, 90 degrees in direction of rotation, to keep that gyro level. That, folks, is the inner workings of the attitude indicator. Now, what about that heading indicator? Remember on the earlier video, we had talked about that heading indicator rotating in this vertical plane. And you can see that right here. You can see that on the diagram. This is the vertical plane, and on the top of that diagram, do you see that main drive gear? All right, I have taken this paper plate and now simulated that main drive gear. Now, once again, this gyro is in a gimbal. And the gimbal is attached to the instrument case attached to the instrument panel, and the panel, of course, is attached to the airframe. So the airframe, the instrument panel, and the case are going to move around this gyro, which, because it's rapidly spinning, has rigidity in space. This gear up here is geared to the compass card on the face of the heading indicator. So if you can imagine the heading indicator around this gyro, and my hand will be the face of that instrument. As we change heading, the aircraft moves around this gyro. See that? And this gear is now gearing and turning this compass card, which is, in this case, my hand. You see that? It's moving around the instrument. Okay, so this maintains rigidity in space, and the compass card is geared to this horizontal main drive gear at the top. And as it moves around, we see a change in heading. Okay, that's the heading indicator. Now, what about the internal workings of the turn and slip and turn coordinator? Well, let's start with the older turn and slip indicator. Now, in this slide, you see the turn and slip indicator on your left. Now, notice, once again, here we have a horizontally mounted gyro spinning at a high rate of speed. Now, my pencils here are representing the mount for this gyro. Now, when this gyro feels the yawing effect of the aircraft changing heading, it's feeling that force here, right, or here. Now, in gyroscopic precession, that force actually acts 90 degrees in direction of rotation. So if it feels the force here, it moves 90 degrees in the direction of rotation, and it acts right here. You see that? So it feels the yawing force here, gyroscopic precession moves it here. Now, the stronger that yawing force, the stronger the precession, the greater the tilt of that gyro, and the further it deflects that horizontal white bar, okay, halfway to the doghouse, or all the way to the doghouse, or past the doghouse. And it's calibrated such that 3 degrees of turn per second line up the white bar to the doghouse. Okay? Well, what was the big advantage and the big change of moving from the turn and slip indicator to the turn coordinator? Now, you've probably heard many pilots, flight instructors, etc., talk about the fact, well, on the turn coordinator, there's a 30-degree cant, and now it can sense both yaw and roll just by canting at 30 degrees. What happened? Okay, take a look. It's still vertically mounted and it's rotating this way, but now I'm going to take these gyro mounts, these are my two pencils, and I'm going to tip them up 30 degrees. Now, what about when I yaw the airplane? Just like the turn and slip indicator, okay, that force will be felt here or here. Let's say I feel that force here as I yaw it, 90 degrees in the direction of rotation. Yep. I still have my rate of turn on the turn and slip indicator, all right? But what if I bank the airplane? So I put a rolling force on this gyro, and that rolling force is felt right here, but gyroscopic precession causes it to act right here, and now the gyro can move this way as well, and that's the movement that tips this little white airplane to the left or to the right. So by taking this gyro mount and tipping it up, I can allow yaw to still give me rate, but I can allow roll to now give me bank. And I can see that on the little white airplane. That is the internal workings of these three gyros. Well, folks, I hope this rainy day exercise and a little bit of arts and crafts with some plates and cups has helped you understand the operation of these instruments more thoroughly. Please join us next time.